learn about ArrayList and LinkedList. These are the two powerful ways of storing data in Java. And the better way to understand them is simply by building a shopping cart system. So what's the difference between ArrayList and LinkedList? Think of ArrayList like a shopping basket. You can add or remove items and it's super fast when you're accessing by index. Like give me the second item. And LinkedList, think of it like a conveyor belt in a grocery store. Each item is linked to the next one. It's great when you want to add or remove items frequently in the middle of the list. So ArrayList is for fast lookups and LinkedList it's for fast insertions and deletions. So let's build a shopping cart with ArrayList. Import java.util.arraylist, public class shopping cart ArrayList, public static void main string args, ArrayList string cart equal to new ArrayList, cart.add milk.add bread, eggs, apple, system.out.println cart items plus cart. And to remove items, cart.remove bread, system.out.println cart after removing bread plus cart. And in order to access items, system.out.println first item plus cart.get0. To loop through the cart, system.out.println final cart. First string item cart, system.out.println dash plus item. And the output will be cart items, milk, bread, eggs, apple. Cart after removing bread, milk, eggs, apple. First item, milk. Final cart, milk, eggs, apples. Now let's build a shopping cart with LinkedList. Import java.util.linkedList, public class shopping cart LinkedList, public static void main string args, LinkedList string cart equal to new LinkedList, cart.item milk, bread, eggs, apple, system.out.println cart items plus cart, cart.add first bananas, cart.add last orange juice, system.out.println cart after adding bananas and orange juice plus cart. Remove the first item, cart.remove first, cart.remove last, system.out.println cart after removing first and last plus cart. And the output will be cart items, milk, bread, eggs, apples. Cart after adding bananas and oranges, bananas, milk, bread, eggs, apples, oranges. Cart after removing first and last items, milk, bread, eggs, apples. In here, ArrayList is like a basket where you know positions. Great when you often need to fetch items quickly. And LinkedList is like a chain of items. Great when you need frequent insertion or deletion from the middle. To HashMap and HashSet, two super useful tools in Java. So what are they? HashMap. Think of it like a dictionary. You have a word and the count of how many times it appears. HashSet. Think of it like a basket that only keeps the unique items. If you put any duplicates in it, it ignores them. Let's think of an example. When you write a text, apple, mango, banana, apple, HashSet will give apple, banana, mango, only the unique words in it. And the HashMap, it will give apple equal to 3, banana equal to 2, mango equal to 1. It counts how many times a word is repeated. So let's write a code for word frequency with HashMap. Import java.util.hashmap, import java.util.scanner, public class word frequency, public static void main string args, scanner is equal to new scanner system.in, system.out.println, enter a sentence, string text equal to sc.next line. We need to split the sentences into words. So string words equal to text.split. We need to create a HashMap. HashMap string integer word count equal to new HashMap. We need to count the frequency of words. So for string words, word equal to word dot to lowercase, this will convert into lowercase. If word count dot contains keyword, word count dot put word count dot get word plus 1, else word count dot put word 1. And we need to print the results. So system.out.println word frequencies for string key, word count dot key set, system.out.println key to word count dot get key, sc.close. And the output will be enter a sentence. Apple, banana, apple, mango, banana, apple. Word frequencies apple 3, banana 2, mango 1. Let's do another example for HashSet. Import java.util.hashset, public class unique words, public static void main string args, string text equal to apple, banana, mango, banana, apple. String words equal to text.split. HashSet string unique words equal to new HashSet. For string words, unique words dot add word to lowercase. System.out.println unique words plus unique words. So the output will be unique words apple, banana, mango. HashMap is used when you need fast lookups like word counts, storing user details by ID, or even building directories. And HashSet is used when you need only unique items like keeping track of registered emails or preventing duplicate usernames. Stack and queue. These are everywhere in real life, even if you don't realize it. So, what is a stack? Think of a stack of plates in your kitchen. You can only add a new plate on top and remove the plate from the top. So, the rule is last in, first out. Example in computers, undo button. The last action you did is the first action that gets undone. What is a queue? Think of a queue at a ticket counter. The first person who enters is the first one who leaves. So the rule is first in, first out. In computers, printer jobs. The first file you send to the print gets printed first. Let's do an example, undo and redo simulation with stack. Undo stack keeps track of actions you have done. Redo stack keeps track of actions you have undone. Import java.util.scanner, import java.util.stack, public class undo redo, public static void main string args, scanner is equal to new scanner system.in. Stack string undo stack equal to new stack. Stack string redo stack equal to new stack. While true, system.out.println choose an option. 1 do action, 2 undo, 3 redo, 4 exit. Int choice equal to sc.nextInt, sc.nextLine. Switch choice, case 1, system.out.print, enter action. String action equal to sc.nextLine. Undo stack.push action, redo stack.clear. Once you do a new action, redo history resets. System.out.println, action done plus action. Break. Case 2, undo. If not undo stack dot is empty, string undone equal to undo stack dot pop. Redo stack dot push undone. System.out.println undone plus undone. Else system.out.println nothing to undo, break. Case 3, redo. If not redo stack dot is empty, string readone equal to redo stack dot pop. Undo stack dot push redone. System.out.println redone plus redone. Else system.out.println nothing to redo, break. System.out.println exiting. sc.close return default system.out.println invalid choice. So the output will be Java, TreeMap and linked HashMap. While TreeMap automatically sorts the keys in ascending order, linked HashMap keeps the keys in the same order you inserted them. We'll use them to build a student marks leaderboard. So why TreeMap and linked HashMap? Imagine you have student marks Alex 85, Mia 92, John 75. If you want to see students sorted alphabetically, TreeMap is perfect. If you want to see the students in the same order you inserted them, we need to use linked HashMap. So let's write a Java code. Import java.util.star, public class student leaderboard, public static void main string args. Let's use the linked HashMap to keep the insertion order. Map string integer linked marks equal to new linked HashMap. Linked marks dot put Alex 85, Mia 92, John 75, Sarah 88. System.out.println leaderboard leader HashMap input order. For map.entry string integer entry linked marks dot entry set. System.out.println entry.getKey plus 2 plus entry.getValue. System.out.println leaderboard TreeMap sorted by name. Let's use the TreeMap to automatically sort by student name. Map string integer tree marks equal to new TreeMap linked marks. For map.entry string integer entry treemarks.entry set. System.out.println entry.getKey plus 2 entry.getValue. System.out.println slash n leaderboard sorted by marks high to low. Let's sort by value marks. Link marks dot entry set dot stream dot sorted a comma b to b dot get value dot compare to a dot get value in order descending order dot for each entry to system.out.println entry dot get key plus 2 entry dot get value. So in here linked HashMap keeps the order of entry. TreeMap automatically sorts by key. With streams you can sort by value like marks. Custom sorting. Java already sorts numbers and strings. But what if we have our own objects like users with name and age? We need to teach Java how to compare them. So let's set up our problem here. Imagine you have a list of users. Alex, age 25, Mia, age 22, John, age 30. Now we want to sort them by age, like from youngest to the oldest, and sort them by name, alphabetical order. That's where comparator comes in. Let's create a user class here. Let's sort with comparator. And the output is original list: Alex, Mia, John, Sarah. Sorted by age: Mia, Alex, Sarah, John. Sorted by name: A to Z: Alex, John, Mia, Sarah. Sorted by age: oldest first, then name: John, Alex, Sarah, Mia. Arrays in Java. So far we worked with normal arrays, one line of data like array of 10, 20, 30. But what if we want to represent something like a chessboard, a tic-tac-toe game, or a Sudoku grid? That's when we need 2D arrays, basically an array of arrays. So what is a 2D array? Think of a Sudoku board. It's a 9 by 9 grid. Rows left to right, columns top to bottom. A 2D array looks like this. Int row column Sudoku equal to new int 9 9. First 9 is the number of rows, second 9 is the number of columns. So this makes a 9 by 9 grid, just like our Sudoku board. So let's put some numbers inside like a partially filled Sudoku puzzle. For int I equal to 0, I less than 9, I plus plus. For int j equal to 0, j less than 9, j plus plus. System.out.println board ij plus space system.out.println, and that's the output. Here 0 means empty cell. That means it's not filled yet. And the other numbers are Sudoku clues. So why do we need to use 2D arrays? It's perfect for grids, tables and boards. Sudoku, chess, tic-tac-toe and even pixel images can be stored as 2D arrays. Talk about matrices in Java. A matrix is just another word for a 2D array. But here we use it for things like math operations, additions, multiplications and even images. So what is a matrix? Imagine a grid of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 3 by 3 matrix, so 3 rows and 3 columns. In Java, it's just int row column matrix equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Why images are matrices? Think about a black and white image. It's just made of pixels, tiny squares. Each pixel has a brightness value. 0 is black, 255 is white. Values in between are just shades of grey. So 100x100 pixel image can be stored as 100x100 matrix of numbers. So int row column image equal to 0, 255, 0, 255, 0, 255, 0, 255, 0. This tiny 3 by 3 image would look like a plus sign made of white pixels on a black background. Let's try matrix addition. Suppose we have two 2 by 2 images. Public class matrix operations, public static void main string args. In matrix A equal to 1, 2, 3, 4. In matrix B equal to 5, 6, 7, 8. In matrix result equal to new int 2 by 2. So matrix addition, for int I equal to 0, I less than 2, I plus plus. For int j equal to 0, j less than 2, j plus plus. Result matrix ij equal to aij plus bij. And let's print it. System.out.println matrix addition. For int I equal to 0, I less than 2, I plus plus. For int j equal to 0, j less than 2, j plus plus. System.out.print result ij plus space. System.out.println. And the output will be matrix addition 6, 8, 10, 12. So why this matters? It matters because we use it almost every day. It's used in image processing, AI and machine learning, and even on computer graphics. Every time you apply a filter on an image, you are doing matrix operations on pixel values, like blur or brightness increase, decrease. Images, speech, even text are stored as matrices before computer understands them. Rotation, scaling, and transformation all depends on matrix multiplication. About object arrays in Java. Arrays usually hold simple data types like int or string. But sometimes we want to store more complex data, like a list of products, each with a name, price, and quantity. For that, we use object arrays. First, let's create a product class that stores details for each product. Class product, string name, double prices, int quantity, and let's use a constructor here. Product string name, double price, int quantity, this dot name equal to name, this dot price equal to price, this dot quantity equal to quantity. And let's use method to display product info. Void display method, system.out.println product plus name, price plus price, quantity plus quantity. Now we make an array that stores product objects. Public class product database, public static void main string args, and let's create product array of size 3. Product array of products equal to new product 3. Product 0 equal to new product laptop 99 5. Headphones 49 20. Smartphone 79 10. And let's display all products. For int I equal to 0, I less than products.length, I plus plus, products I dot display, and the output will be product laptop, price, quantity, product headphones, price, quantity, product smartphone, price, quantity. So why this matters? Objects arrays let you store complex data instead of just numbers or text. You can store multiple objects in one array and process them easily. This is how real-world apps manage product catalogs, user lists, and more. How to search and sort data. These are two of the most common operations in programming. So what is searching? Searching means finding something from a list. Imagine you have a list of numbers like 10, 20, 30, 40, 50, 60, 70, and you want to find out where 40 is. There are two main types of searching: linear search and binary search. Linear search is a simple one. You can check each number one by one until you find what you want. It's easy but slow if your list is big. Binary search is a smart one. It only works if your list is already sorted, but it's super fast. Let's take our sorted list again. We're looking for 40. In step 1, directly look at the middle element. Here it's 40. Boom, we found it in the first step. But let's say we are searching for 60. Step 1, middle element is 40 and 60 is bigger. Is 60 bigger? Yes. We ignore everything on the left side, 10, 20, 30, 40. Step 2, now we search only the right half, 50, 60, 70. Middle element is 60 and we found 60. See, we didn't have to check every number. We cut the list in half each time. That's why binary search is much faster than linear search. What is sorting? Sorting means arranging data in a particular order, usually from smallest to biggest or alphabetically from A to Z. For example, if you have prices like 50, 10, 30, 70, 20, sorting will rearrange them into 10, 20, 30, 50, 70. Why do we need sorting? Because most searching algorithms like binary search need data to be sorted first. Also, sorted data is easier to read, compare, and analyze. Let's start with the simplest sorting algorithm, bubble sort. It's called bubble because small elements slowly bubble up to the top, just like air bubbles in water. Here's how it works. Compare the first two numbers. If the first number is bigger, swap them. Move to the next pair and repeat. By the end of the first round, the biggest number will move to the last position. Then repeat the process for the remaining elements again and again until everything is sorted. It's slow for big lists but perfect for understanding how sorting works. Let's imagine you're making a small e-commerce app. You have a list of product prices and users want to search them from lowest to highest. That's sorting. Now they have a price and want to see if the product exists. That's searching. So both searching and sorting go hand in hand in real world applications. Recursion. Recursion is when a function calls itself to solve a problem. Think of it like Iron Man's AI, Jarvis. When you give it a task, it keeps breaking it down into smaller tasks until it's done. That's exactly how recursion works. So what is recursion? Let me give you a real life example. Imagine you have a set of Russian dolls, each doll inside a bigger one. You want to open the smallest doll. Instead of opening all at once, you open the biggest, then the next, and so on until you reach the smallest one. Each step calls the next smallest step, just like recursive function calling itself. In programming, recursion is used to solve problems by breaking them into smaller versions of the same problem. Example, factorial. Factorial of a number n is the product of all numbers from 1 to n. For example, 5 factorial equal to 5 into 4 into 3 into 2 into 1, which is equal to 120. Now, instead of multiplying manually, we can use recursion. So factorial of 5 equal to 5 into factorial of 4. Factorial of 4 equal to 4 into factorial of 3. This keeps going until factorial of 1 is 1. Let's write a code for it. Public class factorial example, static int factorial int n. If n equal to 1, return 1. This is a base case. Return n into factorial n minus 1. This is a recursive call. Public static void main string args, int number equal to 5, int result equal to factorial number, system.out.println factorial of number is result. If you run this, it will print factorial of 5 is 120. Notice how the function keeps calling itself until it reaches the base case. Base case is super important, otherwise the function will call itself forever. Backtracking. Sounds scary? Don't worry. By the end of this video, you'll completely get it. Let's start simple. Imagine a rat inside a maze. like those Tom and Jerry cartoons. The rat is stuck in a grid full of walls and paths. Your job? Help the rat find its way from the start to the end. Now there's a twist. The rat doesn't know the way. It tries moving in all possible directions. Up, down, right, left, until it reaches the end. If it hits a wall or dead end, it goes back and tries a new path. That going back part, that's backtracking. So what is backtracking? Backtracking is like saying, I'll try one option. If it fails, I'll go back and try another. It's basically recursion with a decision tree. You explore all possible paths until one works. Imagine you forgot your phone password. You try one number combination and it fails. You delete and try a different one. Again it fails. You keep trying different combinations until you unlock it. That's backtracking in real life. The maze problem. We'll represent the maze as a 2D grid. 0 means blocked, 1 means path you can walk on. The rat starts at the top left corner 0, 0 and needs to reach the bottom right corner n-1, n-1. And let's write a code for that in Java. Let's understand what's going on step by step. We start at the top left cell 0, 0. If it's a valid path 1, we make it in our solution matrix. Then we try to move forward, first down, then right. Every time we move, we check if the cell is safe, not outside the maze and not blocked. If we reach a dead end like 0, we go back. That's the backtracking part. When we finally reach the bottom right cell, we print the path. If no path exists, we print no path found. And the output will be 1 0 0 0 1 1 0 0 0 1 0 0 0 1 1 1. The ones show the path the rat took to reach the destination.